Hello everyone. I want to make sure everything works. Perfect. Welcome to this new stream. The objective today is simple. We want to complete the 8x8 multiplier we've started 2 weeks ago. And I'm pretty sure we will be able to at least achieve the part where we simulate with the test bench. And the next stream, if we don't have time today, which will probably be a little tight, we want to make the CPU in the FPGA communicate with our IP, our multiplier. So when we type in the terminal, let's say we send a number, hit enter, send another number, hit enter again, and the CPU, the program that runs on the CPU, will take those numbers, send them as 8 bits integer, wait for the answer back, and then return the answer to the terminal. So this is the goal for next week. And next week, since this week, in fact, we've started to stream twice a week at the same time. So 8 p.m. EDT, Eastern Time. So I'm in Canada, Quebec. And the other thing is we might be able to start another project and continue the CPU. And we will take a lot more time on the concept of how a CPU works. Now, quick introduction again. My name is Andrew. I'm currently a master's degree student in electrical engineering. I'm very interested in low-level programming, and the FPGA that we are using today is this little beast here, the ZenQ Z7-20, sorry. And it is equipped with 2 ARM core. There's a little, not the smallest, but not the biggest FPGA fabric in there, and a lot of IOs that we can use for any project we want to do. Good. I want to advise everyone that today my kids are at home, so they could be probably interrupting the stream at some point. So I'm very sorry about that. Let's have fun together. Good. So last streams earlier this week, I've completed the MultiplierController here, and we instantiated a lot of the modules we've created earlier. So the full adder, we have a serializer. Don't forget that the serializer receives parallel data and then send 1 bit at a time considering a clock. The shift register takes data, or usually the shift register, what it does is it receives data and fills the register, and then it's like the opposite of the serializer. So it will fill 16 bits for instance, and then we will take those 16 bits and manipulate them. In this case, it's a little bit different. What we do is we load 8 bits of data, and in those data what we do is shift it to the left, so we add zeros at the right of the register, so we can use this value to simulate or implement a way to multiply. So if I go to the drawing board here, let me grab my mic. Okay, so you remember when we want to add numbers, either number that are decimals or binary, we will have, for instance, those bits. So let's call this A and this B. And what we will discover is that every time we have a 1, we copy those values, below. Okay? And the shift occurs because when we come to the second number here, we need to fill a 0 over there. So this is why we need to shift register towards the left, so we pad zeros to the right. And since this is a 1, we recopy all of those numbers again. 1 1 0 1. We have a 1 here, so we copy 2 zeros now because we are the third one here. So we recopy 1 1 0 1, and since this is a 0, we can extrapolate that all of this row will be 0. So when we add this, we have 1 here. We have 0 carry 1, 1 carry 1, 1 carry 1, 0 carry 1, 0 carry 1, 1. So let's calculate if we have the right answer. So this is 11, this is 7, we have 77. So here we have 1, 2, 4, 8, 16, 32, 64. So we have 64 plus 8 plus 4 plus 1. It's equal to 72, 76, 77. So we have the right answer. Let's go back here. Okay, so this is the module that will shift those values to the left, and when we feed our full adder those values, it will do the addition like I did. Good. Just a second, I want to make sure here, like such, like this, and we go here. Perfect. Okay. So now, what do we do? Yes, the multiplexer. So the multiplexer takes 2 inputs. In this example, we have 1 bit that select which input goes to the output. It's a way to route multiple information into a single bus if you want. And this will be used in 2 places. So if we look at the circuits I draw here, like this, can we hide this? No, okay. So I did this schema here, and this is not the actual implementation we did. Those two register over here are not in this current design, the current code we have over here. Wait a second, I will find this. So this doesn't have the register we saw earlier in this design. But we will need those because right now this here is connected to operand 1, and the sum goes to this mux and over to operand 0. 1 minute, please. Okay, so the problem we have is this, and this are combinatory component. So at the moment something changes, everything is computed virtually instantly. Okay, so this is a problem because just think about it. If the sum over there goes back to operand 0, it means that the sum will change operand 0. So instantly sum will change and then go back to operand 0 and goes round and round. And this is a problem. What we want is that at every single clock cycle, we want the value operand 0 and 1 to change to compute the new value. So those register our flip-flops, it's their responsibility. They will receive eventually some either 0 or some S sum, and at the clock cycle, then it will change. So there won't be an effect of an like it's kind of like an infinite loop in the sense that if you don't have the clock, the value change constantly, and it's the same thing here. So, and now what we need to do is those signals, like this one for instance, is called, I think, S shifted, and this one is called, let me look back to my code here. So if we look at the output S shifted, and this goes to operand 1, that is in fact I think A, and now we want the full adder to go to 0. So sorry, it's the inverse. So S shifted goes to the B, and A full adder A receive this signal. Okay, so let's do this. We need first to create the entity. We go here, we create this, create a file, register 16-bit. Okay, finished. It will be RTL and ports. So usually it will be D flip-flops. So we don't go there today. We might take sometimes in the future to go about all the different kinds of flip-flops we have. So this is 15.20. There's a reset signal, which is setting the register to 0. There is a clock that syncs the moment when we change the output to the value in the input, and usually the output is called Q. So D is the data, Q is the output. So we say OK. And now it's pretty simple. We create a register of type STD logic vector of 16 bits. And what we do is pretty simple, is that we create a process that follows the clock. And if rising edge of the clock, then if, and now we want to, if reset is asserted, so set to 1 in that case, we want the reg16 to be set to 0. So at the next clock cycle, then it will Q will be 0. If reset is not 1, then we set reg16 to the value in D. Okay, so if reset is 1, then we say that reg16 receive all zeros, others 0. Okay, don't forget, we can use that syntax to fill all the register of zeros. I could have set 16 zeros, but this is really often used in VHDL code. It's a way to set to 0 that is less cumbersome than writing 16 0 or X 4 zeros, stuff like that. Okay, so if it's not asserted, now we want reg16 to be equal to D. And now at the general process, what we want to is that Q is connected to reg16. So now I think we are okay. Reg16 receive D. What is the error here? We have what's the problem? Okay, so if rising edge if reset equal, then pre-existing receive this, else if, yeah. I have so many, it's so hard for me to see else if in that way, like in the fact that there's no E there, I always think there's an error. Pre-existing receive D, and if I don't get the error. What is it? Near the semicolon. Okay. Why? This says syntax near if rising edge clock, then if reset equals 1, then rec16 receive others. Oh, it's just else. Yeah, sorry. Oh, I was tired. Okay, so now rec16 receive the input D, and then rec16 is connected to the output Q. So all of those values will only change at the rising edge of the clock. Good. So now we can take all of this here and put it back to our multiplier controller as a component, like so. Change component here. I like to put a component here. Good. So if we go back to our schema here, we have shifted here. So this signals don't change. We don't really care about it. Now we have this signal is S sum. Whoops. Why it doesn't work? S sum, like this. This go over there, and this was the output. If I go back over there, it was S full adder A. So S full adder A now connects to our S adder full adder. Is this correct? Going back over there. So it's S full adder A. Okay. A. So now what we need to do is we will need two new signals. In fact, there is a little more than two, but we will need one signal here that we will call a S full adder buff. And this will be called a S shifted buff. Okay. Let's move this over there. Okay, that's good. So what we'll do now is go back to the code here and create our two buffer. So buff 0. It's a register 16. Like this. And port map. Now, the input will be this. We will need a new reset signal. And the reset signal at the start of the process will probably be the value 1, meaning that we want if we are in waiting, we want everything to be cleared. So the reset will be 1 and those register will be set to 0. So it won't be a constant though, it will be like this. S reset. Let's create another line. Signal S reset std logic. It will be equal to 1. So at the start of our process, we will have all of our flip-flops set to 0. So S reset goes over here. We will have the clock. It's a signal we receive into the our controller over there. So this is easy. And now we want to send a S full adder buff, and this one goes over there. So now if I go up to find where I define my S full adder, I can create my S full adder buff here. So what I did now is connect. I disconnected this output over there to there. I connected it to this second buffer, and this is then connected to our operand one here. Okay, now we can do the other one, buff1 register 16-bit port map. Okay, now what we will get over there is the SSUM goes in here. So what it means is that this one will be our S. Well, I don't remember what I called it. Full adder buff. S full adder buff. No, false. This is false. This I did. It's already put at the over there. Okay, no. Why did I call it full adder buff here? It's the shifted buff here. S. Oh. I pointed the wrong buffer for the time, but I did the first one. I connected this here to this and to this one here. I didn't connect the other one. Sorry about that. Okay, now we will do this one. So now we want the shifted goes here. So this is the shifted buff. So now all we have to do is S reset CLK buff. That is the way. Now, okay, S shifted buff is not defined. What we need to do is put it there for to be able to follow the code. In fact, I just want to tell what I'm doing right now is it's the first time I do the 8-byte multiplier on my own. I didn't even check how it is usually done. I'm not even sure if it's the correct way, but it seems to be like a logical, naive approach for this kind of module. And after, when we will make everything communicate together, so the CPU on the Zinc queue will be able to receive information from the terminal, send it to our IP, then receive the answer back, and then send it back to the UART console. We will probably do a refactoring of the code and having a little bit of better convention. Sometimes my keywords are in caps, sometimes it's not. Sometimes some of my variables are like ear clock or reset are in for input, or sometimes I use the not a small name. Sometimes I have even input in caps, which is not usually how we do things. But now we just playing, okay? I didn't want to like take a bunch of time just to figure out and explain conventions. Okay. So now we've connected everything together. Does it have impact in our code here? Yes, it does. So first of all, what we need to make sure is that at the step 1 here, we want reset to be set to 0. So SRST will go to 0. And if I go at final step, we want it back to 1. So R reset goes back to 1. Like such. Okay. And it will stay the same. Now, is there any other signals we need to handle? If I go back here, so reset clock, everything, clock is received to the controller, so we don't have to deal with it for now. We have mux one cell that is already handled also. What else? We had the serial out goes to the select of the first, second Moxie over here. So I think we have everything. So we are now at the point where we want to make a test bench. Let's do this. We go over there, simulation, create, TB multiplier controller. Okay, finish. Okay, yes. Let's put it as a top right away so we don't have any bug later. We don't have ports, and now the only thing we need over there is the definition of our component over there. So we go to the top, we copy this, go back to the test bench, paste, and it crashes, of course. Vivado. Vivado. I didn't have time this week to find out how it managed to do those problems. Oh, this is not the right one. This is it. All right, won't be too long. Okay. I like this. We go to simulation. We go over there. Now we're ready. Okay, so this is a component. Like so. And we will need those signals. So what I do very so often is copy this. There. We align everything. And we add the information. So one of the tips, if I hold Control Shift, I think I can put multiple cursor over there. Signal S underscore, and we remove all of those keywords because we can imagine those as wires. Don't forget this. Now we will need a period, so a constant period of type time with the value 10 nanoseconds that represent 100 megahertz. Blazing fast. Okay. So now what we need to do? We need to do the UUT. We need to process to simulate the clock. And now a process to do calculation. And make sure everything works as intended. So UUT, it's a unit under test. We will call multiplier controller port map, SA, SB, S multiply, SCLK, S product, S done. Good. How do we do our process? Begin and the process. So the process for the clock, what we do is we wait for period divided by 2, and after that we do the inverse of the current clock. So SCLK receive not SCLK, and we make sure that everything over there is initiated to zeros. So others 0, poof, poof, 0. So when it starts, it will be 0 after period 1, 0, 1, 0, 1, 0, 1, and so forth. Okay. And now we are now ready for our process. Okay. So process, begin, and process. So 0 times 0 is 0. So let's wait for period and move on. So we will make sure that the 0 times 0 works. Now let's try by changing either the A. So SA receive, let's say, X that beef, like such, and wait for period. Again, it should be 0. Let's put back 0 to... Oh, sorry, it's just it's 2 letters. So let's say 5A over there. Now 0, 0. I forget that we are working with only 8 bits. And SB will be A5. Oh, we have Samrod the DOD that leave. Sorry, it's that I think I don't know if you already gone, but it was fun to have you on the stream. Wait for period. Okay, so right now we want to do a real multiplication. So let's put SA equal to X0B. So it's 11, the value I did earlier. Let's put SB equals to 7, which is also 7 in a decimal. So we should have 77 as an answer, or in I have it over there, just a second. Okay, so if you want to know how we can convert binary to hexadecimal, so we group our uh, binary values in groups of 4, and it's pretty much, it's not easy, it's just you have to be accustomed. But 1010, it's 10, so it's A. So if I go one more, it's B, and like this it's C, and like this it's D. So this is D, and this is the value 4, because we have 1, 2, and 4, so it's just the 4. Then 77 in decimal is equal to 7D in 4D in base 16, so hexadecimal. And I know it looks like a 0. I will try to put it a little bit better. D 16. Perfect. Going back to the screencast. So now what we want to do is wait for period, and let's try only that. It's simple. It's not that big of a test. It shouldn't be too long to run. Let's see if Vivado will give me the permission and be so kind to let me test and run the simulation. Indeed, it doesn't work. Why? Because we crashed earlier, remember? And when we crashed, not all of the process died. So let me go back to my task manager and go over there. And here it is, this little goblin, like with some people like to use. Okay, now restart our Vivado. Let's open the project. Okay, is it done? Can I run simulation? I will try. I will wait a little bit just to make sure everything is loaded. Run simulation, and it started. Okay. So product doesn't seem to change. Oh, did I change it? So let's zoom a little over there. We have 0, 5A, 5A, 0B. and then we go back 5. Okay. All right, and we have a S done that is set to undefined over there. Okay, there are still some stuff we need to fix. So I didn't connect, it seems, the S sum to the output. So if I go back, or maybe because I set it to 0 over there. So since I reset over there, okay, so now what I need, S sum goes to S product, and S sum is the output of the full adder here. But since I reset, I need to reset in waiting. I need to reset that waiting. So waiting, reset. I cannot reset because the adder will then be set to 0 and the sum will go to the... and this is not what we want. So let's try this now. Run simulation. So S product get S sum and S product goes to product. And run. Okay, we still have zeros and it doesn't change much at all. Do we have a done? The done goes to 0 and stay there. So we need to see the state of our module. Okay. Seem to have... I want to see the state of our entity, but I cannot find the entity over there. Why such? Why so? Oh, it's over there, I think. Yeah, I need to go here. No, let's go to simulation. Okay, yeah, it's here. So if I go inside this UUT, we will have all those signals and we will have the state. So let's put the state and rerun the... So let's go back. Let's run for, let's say, 1,000 nanoseconds, just to see if we can see things. Okay. So it's always on waiting, and that is a problem. Oh, yeah. Okay, okay. So there's something we forgot. The test is a little bit more complicated. Yeah. Okay. Let's go back to stream code and go open our mini tests. I was a little bit too motivated. So in order to make it work, we need to set S multiply to 1. Then we wait for period times, let's say 10 for now, because I think there is only 8 steps. But just to make sure there's no problem, we will do a times 10, and then we set S multiply back to 0. In fact, what we could do, since we don't require multiply to be asserted all the way, we can say period once, S multiply goes back to 0, and then we wait for period times 9. So this will be required every single time we want to do a test. Like this, and like this. Okay. Is there any problem? I don't think so. Okay. So now let's rerun a simulation. Discard. Oh, there's errors. Why? Okay, let's go to tickle here. Let's go over there. It's what VHDL.log. VHDL.log open. Going back. It's going down for real. Okay. Now, physical unit doesn't denote the physical type. Line 82. Line 82. It's in the test bench or the... Yes, the test bench. Line 82. Oh, yeah, sorry. We need those semicolons. Okay, let's try again. Okay, so now let's go back to simulation. Let's make sure we know our states. We want the states to change. Say where? Oh, over there. State. Rewind and 1,000. I think it's appropriate. Okay. Oh, I think I saw it changed. Yeah. Oh, I think I did too much time. Let's pause and go back over there. Okay. So let's zoom out. God. 1,000 nanoseconds. And those are milliseconds. Something is wrong. Okay. Let's go back at the start and let's zoom in. Boo, 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 boo. Okay. Damn. Can I go home? Okay, let's take this one. Oh, this is a clock. This is the period. Okay. Let's zoom. Over there. Yeah, okay. So we started the multiply over there and the state started to change. So it seems to be working. So we now have loading, step 1, step 2, step 3, step 4, 5, 6, 7, final step. So now at that point we have 0. We don't know if it works or it's just a coincidence. So let's go and continue. Waiting, step 4, 5, 6, 7, final step. We still have 0. Okay, now we shouldn't have 0. So waiting, loading, step 1, 2, 3, 4, 5, 6, 7, final step, and we still have 0 here. So let's look at those signals internally. We need to know we want to know, for instance, S sum, S shifted. We want the S full adder buffer and S shifted buffer. Let's keep this one and go back. Let's. I think it's because I need to use this one. Okay. So we will try to. Oh, I think it worked here. So okay, no. So we have the shifted here. We have a B. Then it's going back to 0 over there at step. So there's something wrong with those signals that appear. So shifted here, we see that the 0 goes over there, but it doesn't seem to be shifting. Okay. So why doesn't it shift? We have a CLK also, a CLK, yeah. This is our test bench, and okay. So what I want to do is remove all of this. A, B, multiply, clock. We want to see product. We want to see done. We want to see. So we see that SA seems to have shifted. SA, SB has shifted. As sum, as yes, we want to see if the cell marks change. We want to see the full adder buff as product. Okay. And just so we don't have zeros, we will change the test bench and do this computation first. Like so, it's like so. And we will remove all of the rest. So I'm pretty sure we'll be okay. Okay. Where is my, okay. We go back. Let's play. I think we are okay at 150 nanoseconds. Will be faster. I don't know if I need to redo the simulation. Let's just make sure everything is all right since we modified the code. Okay, this over here. Okay. Now, I want to remove all of this for now. Let's go to the UUT and look at all of this. Whoa. A, B, multiply, clock. We want to know the done signal. Let's look at the product also. S compute, SA, SB, S reset, shifted buffer. We will look at S sum. Let's look at S sum, full adder A and full adder buff. I think maybe I messed up this configuration. I'm not sure. Yeah, and S product. Okay, going back, run, and action. Okay, so let's just make it a little bit less convoluted. Okay, so we have a lot of signals that are not instantiated over there. That means, so if shifted buff is in relation to the register over there, I could put others 0 here. Okay, as sum, so this is the value over there. and it's the output of the full adder. So if I go to the full adder, where's my source? Full adder. We don't have any. Oh yeah, there's a signal, but those are carries. We don't. Wow, we can't set it to 0. Also. Good. Now we have full adder A, which is the output of this one, I think. If we go back in our multiplier over there, we see that full adder, full buff. So full adder A comes from the multiplexer and goes into the register over there, and then the buffer here. So it's the multiplexer. And also the multiplexer doesn't have a internal value over there. So what we need is to make sure that the cell is either 0 or 1, but we cannot know for sure since we are reliant of our schema here. So we are reliant on this output. And serializer 8-bit, serializer 8-bit. We have a reg that we initialize at 0. And we have, oh, what is this? Serializer, it's not the same, it's not at the right place. This is, and oh no, it's okay, it's all right. We want to take we want to take the LSB and then shift all of the values and putting a 0 at the start. So this is correct. Okay. Shift register just to make sure we have 0 also over there. And it's the other way around. We shift all the value to the left and add a 0 to the right. Okay. Now that we've done this, what else can we do? So at the multiply is set to 1 very quickly. The rising edge over there is triggered. And if we go to the states, what's the state? Damn. Okay, let's retry this. So those steps have started. So it's loading at that moment here. So at that point over there, we should see at the output of the serializer and the serializer, we should see Q here and the shift register Q here. Okay, and what we want to see the internal register. So serializer want this one here, and the shift register want this one here. Okay, and so we don't know those values. We need to rerun. Going back, run. Okay, it seems a little bit more promising. So loading here goes to this step there. So in theory, we should see the register here and here having the right value, but we don't see that. We see it at the step 2 over there, which is weird. It shouldn't be there. So there's a delay between the moment we do the loading and the moment propagates to the different component. And at some point we do some shifting and we have a final step over there, which doesn't, and what is really weird is those value doesn't change at all. So there's something wrong with the way we connect all of these values. Let's go back to the code. Okay, let's close our simulation. We will close and go back to stream code. And let's go back one step at a time. Okay. And open the multiplier controller. Okay. So we have a file ladder. We have a serializer, shift register, multiplexer, and register. Sload is compute. Sload is compute. We have SLMux at 0 also. Done at 0, multiply is 1, then we go to loading. Oh, load. So sload is set to 1 for 1 clock cycle. So is it because my load signals go up, stays, but it doesn't go, it goes to 0 over here? Then, okay. So what's going on here? So S load is at 0, S1. Okay. Let's look what is going on around those signals there. So we rerun the simulation. Can I just do this? Run simulation. Okay. So again, I don't really need these signals for now. What I want to see is the S load. Where is it? Here. I want to see shift register load, Q and S reg. Serializer, I want to see load, Q and S reg. S reg. Okay. Okay. Let's do this. Now, what's going on? So, at this moment, S load is set to 1. All of this is set to 1. And if I go back just to look at the clock, yes, we see that the clock is rising over there. And it's the same clock for all of this. If I go there, put the clock is the same. If I go here, take a look at the clock is the same. So all the clocks are connected. Everything is fine here. Now, at the moment we set load to 1 for a period, we see that it takes that 1 clock cycle to have our change in here. So that is first a little weird, since oops, let's go back to the test bench. Okay. So we change here. We set multiply to 1 and then multiply to 0. And we have a weighted period here. Okay. Let's look at multiply. So multiply is set to 1. And then at this point, we see all S load, everything goes to 0. Then 1 clock cycle after, the loads are set to 1. So what we can do about this is in the controller there, when this is true, S load goes to 1. So let's put this here. Else S load 0. So now 0 S load 0 like this. And we remove the resets over there. I don't know if it's still true. We will see. Okay. Let's rerun this. So is it a little bit faster? So now we have our multiply goes here. Then again, we have our loads coming at the next step over there. Then Q. So if we look at Q and sreg, we see that at that point there, the value have changed. So there is a delay in how much time. So since we have, it's weird that this one is at that point, but those are at those points here. I would have assumed it would go there. So what is going on here? So if we go there, the sreg 7, here we see that there are movements. So it starts as 7, then it goes to 3. And if you remember, let's go to the drawing board. What the serializer does is it receives all those bits here, and it will shift to the right and output the last bit of the series. So the first to go out is a 1, and then we put a 0 and remove all of this. So this is 7, this is 3, sorry. Then there will be 1, then there will be 0 for the rest of the process. Okay, and I think this is what we see here. We see 7, 3, 1, and then all zeros. But what I realize is those, yes, those are shifting also. If we go here, we have B, then 1, 6. Let's try it together. So we start with 0, 0, 0, 0, 1, 0, 1, 1. What we do is we move that way. So there will be 1, 2, 3, 1, 0, 1, 1, 0. So this is 1, this is 6. And if I go back here, this is what we get. We go from B to 1, 6. Let's try 2C. So we have 0, 0, 1, 0, 1, 1, 0, 0. This is 2. This is 8. This is 4. This is so equals to 12. It's C. Don't forget that A is 10, B is 11, C 12, D 13, E 14, and F 15. Okay, so all of my register over there works as intended. Okay, so this is working. Why don't we see this in the multiplier? So let's look at the full adder just to be sure everything is okay. Oh, I need to go scope. So okay, no, what we want is to look at the buffers. So here want to see Q and reg, and here we want to see Q and reg. 1 second, please. And I'm back. Okay. Can I just rename this? Okay, we can see this. I want just to change the so I can, oh, color. So let's put this blue and this one blue. Oh, and let's retry the simulation. Okay, so now this is the problem. We don't have anything coming out from the these two there, and it's above 0. Above 0, what is it? Let's go back to there. Above 0. Oh, here. Above 0, it's what is supposed to connect the full adder. Okay. So what's going on there? So we have mux1 here. This mux receive some over there, and then this goes to full adder A. This the register over there, flip flop, and this one is then connected to the operand 0. So this makes sure that at each clock cycle, the value of the sum that enters there is not like feeded constantly and cascade the sum to be performed all the way. Okay, so what there seems to be a problem with the way we handle this. I wonder, is there a problem with the other one? And if we look here, we have B that comes from over here with a delay, but it doesn't change after that. And this is a problem. So there's a problem with our register. It seems. It's so if reset is 1 reg and otherwise this. Okay, let's look at reset. Okay, so we have reset up until that point, and then we have a reset over here at the end of the steps. Like not really at the end of this, but this is not what we want. We want to keep the reset and reset at some point over there. Okay. So why? What is happening? So the if reset is 1, reg receive all zeros. Otherwise, reg receive D. And Q receive reg 16. Okay. I don't see any problem with this. So let's go back to the multiplier. Register 16, register 16. So we have shifted, which comes from the multiplexer. This is what we want. We have the reset signals, the clock, and the buffer that goes to the adder. SLS goes out from the second mux. Reset, clock, full adder buff goes there. So we don't have a carry. We take the sum as the second input. SLMux goes to 1 at step 2, which seems to be right because we load the values, then we start computing. But oh, this one, I think I need to compute. Okay, this goes here, but it doesn't change the fact that my values over there doesn't change. This is not normal. So what's happening here? Okay, I can put names. So this is the buff 0. Buff 0. Oh. Buff 1. Buff 1. Okay. So there's something fishy in here, and I don't know why. If I go to my register buff and look at those clocks, yeah, doesn't change. Resets, doesn't change. Let's run this. So why D is set to 0? Okay, maybe we have something there. Let's look at this one. D. So this one goes. This one goes over here. Okay. So D changes weirdly. Okay. Let's go back there. So D comes from the mux here. We have this mux here, and this one goes to B0. To 0B, sorry. And then back to 0. Okay. And B0 is full adder. And B1 is shifted. So FA. FA. shift, shift. But it's not supposed to be that because here I set A as 0B and 0.7. So it looks like this is inverted in some ways. Shift register receive A. It's just supposed to receive B. And this is A, SB, SA. And then SA. Oh, is it? No, I don't think it's a problem. It should work anyway. Oh yeah, it's on the same. Okay, yeah. Oh, it's. What's going on? Undo, undo. Okay. In fact, I don't think it's a problem. The serializer and the shift, they can be changed independently. Doesn't matter. Okay. It's still B. Why? Is this the right one? Buff 1, buff 0. FA. SHFT. I don't understand why it's always B over there. It's not supposed to be B. And it's supposed to shift, and we saw it shift right here. Right there. It's shifting here. So this is what happened in the shift register. This is what is, so this is the output, and this output goes to, so this is the Q of the shift register. If I go back here, shift registers, the output is SA. SA goes to the multiplexer here, becomes S shifted. Yeah, it's in one cell is SB that define if you take 0, 1, then the Q. Okay. I'll take a sip of water. Okay. Why is this happening? So I guess we'll need to do baby steps and make sure all the test bench we have works as intended. So I will go back here. And let's take the full adder 16 bits test bench. Set as stop. Okay. So what we do is a bunch of addition over there. This overflows. This overflows. This overflow. And we even can like copy this, and we set it to 0 and it to 1. It should also overflow. So let's try this. Okay. Let's close this. Yeah, closing simulation like I didn't do it 3 seconds ago. So much fun. Okay. Run simulation. Over there. Let's zoom this. Zoom. So we have 000, 6B, 6B, 9D, 9C with an overflow. 1337. We have 7237. Yes. Then 8 plus 6 is 14, so it's a E. We have 1, 9, that is okay. D plus 2 is F. 4 plus C is indeed 0, carry 1. We have B, C, D, and A, B, C, correct. Now we have FFFF gives back FFFE. We have an overflow. FFFF and 0001 goes back to 0 with an overflow. And we have also this situation where we have FFFF again, but with 0, but a carry. So we overflow again at 0 and overflow here, sorry. So we set a carry in. So with the FFFF, we carry out. So I don't see any problem with the full adder for now. So now let's go to another simulation. We want to look at the multiplexer. So let's set this to top. Can I run this and no? So I want to, do I close here simulation? Open, saves, close simulation. Don't show this again. Okay. Did I find it? How to do it? Yeah. All right. We are learning. This is the good part. Okay, now we have this multiplexer. So if you go back to the tests, what we see is we wait for a period. So at first, the select signals is set to 0 here. Then for a period, then it's set to 1. And we wait for a period. We set in at as lead. It shouldn't change the output because we are in cell 1. But then when we sell 0, then we should see lead. So let's go back here and zoom. So we instantiated the 0 to beef and the 1 as dead. And we see that at the start we have beef. So we got beef. Then at 1 clock, not 1 clock, but at a certain point in time, we change the select to 1. Now we're dead. And we changed beef to lead in between. But since we still select dead, we show dead again. And then we go back to lead here. So this is working as intended again. Good. Let's see other. So we did the full adder here. We will try the serial 8-bit, the serial. In fact, let's call this just the serial. So the serial, what it does is so this is a sequential module. Is this our problem? No, it's since we have since this serializer will have its clock, then at the rising clock output its value, and then this value will be fed to eventually the register, the flip-flop register. At that rising edge, does it do something bad? I wonder. Okay, so we set 5A for 2 periods. We then change it to A5 with a load. And I think at this point, we want to test that if we don't set the load to 1, we don't have the output we want to see. Okay, and then here we set back the load at 0. We set data for 242. We compute and for 8 period, but it shouldn't be 42 because we loaded A5. Okay, so let's run this. First, close simulation. Run simulation. That is so cool. At last, my love is coming home. Okay, so now what we see is we want more. We want to see the register. Let's go back. Let's run this. Great. Okay, so we have 0 here. Okay, then A5 doesn't change our A0. Then at that moment in time, we set load to 1. The rising edge of the clock set A5 to the register. So SQ is 1 since A5 ends with a 1. Okay, so at that point we don't compute again. S compute still 0. We change here to 42. It's input, but we don't care since A5 has been loaded, and this is what we will serialize. Now we go here, then we compute. So at this rising edge, we see that A5 becomes 52, which is accurate. 29, which is accurate. 14, A0A, 05, 02, 01, 0. That is perfect. Everything seems to work as intended. I don't see any problem with this. So I don't get why it is a problem with the other part of our code. Let's go back to the source, and since we did this realizer, I think we do this one here. This, what is this? And what is this? Yeah, this is this doesn't exist anymore. Okay, let's remove this like such and go back here. Okay, so now in this process, what we do is set a 5.8. It's basically the same thing. We just make sure that the load works correctly here. There's no problem. We compute. We set this compute to 0. Everything should be working. Let's do this. Close simulation. Whoa. Close simulation. Discard. Then we click, left click, set as stop. We are now ready to rerun the simulation. Okay. Again, I don't see any problem here. So again, here nothing happened because we don't have load set to 1. Load is set to 1. Click A5. Load set to 0, 42. We don't care. Still A5. Then we go compute. So we shift, and at the end we should have A500 instead of 00A5, and this is what we saw earlier here. Okay, that seems to work. So now we have tested the shift register and the serializer, the multiplexer and the full adder. The only thing we've not tested is the register or the flip-flop register, and I didn't create earlier a test bench, so let's create a test bench just to make sure it works. So create here, create a simulation, create a file, pb register 16-bit. Okay, finish. Okay, yes. Please don't crash. I implore you not to crash. So let's go back to stream code to see something. And let's open register 16 here. Copy all of this over here as a component. Like this, and I think I do this. And create all those signals, the RSTQ. Don't forget, you can click Control Shift and multi-select lines, signal S, and then we remove those ins and outs since those are wires, and the semicolon here. Okay, what do? We create our UUT. It's a register 16-bit port map. SD, SRST, SCLK, SQ. Good. Now, process, begin, and process. We want to clock. So wait for period divided by 2. Don't forget to create the constant. And what we do, we inverse our clock signal. So SCLK becomes not SCLK. That reminds us to instantiate it or initialize, sorry, our variables. So others goes to 0. RST receive 0. And this receive 0. And in fact, let's set this to 1. Yeah. I want it to be reset. So what you will often see with reset signals is they are active low. So what it means is it is asserted with a 0 input. So it is 1 for not reset. And I think one of the reasons behind the that concept is that if you have a signals that is with a pull down, I think Don't quote me on this, but I think if it's a pull down, there's a short. It will it will force everything to 0, so it will reset, and it won't. You will be able to detect that there's something electrically wrong. Okay. So now we do the real process of the test bench. Begin and process. So now, what is happening is that as long as reset is 1, I could change SD to whatever value. So A5. Is it for 30? Yes, it's 16. So let's say dead. Wait for period. Then SD gets beef. Now we set SRST to 0. Wait for period. SD receive 42, and that 42 should go to the back of so it should be returned to the output, because our reset is set to 0. Good. So we set this test bench to our, oh, there's an it says there's an error. Why? Set test, I cannot because there's an error, I guess. Where is the error? This is empty. QT register, process, dead beef. Where is the problem? There are no errors near. Oh, did I? What line? 52. Ah, damn. Okay, got it. So we need to set this to top. Booyah. And then we close the simulation. We run the simulation. Okay. We do this. Go back like this. We zoom in. Okay, so we have 0, like we said. Reset is set to 1, so there's nothing happening here. We now have reset to 0, so at that point here, we have beef. At that point, we change our 42, but at that point, the clock changes the value. We go back to dead because we never did reset we never set the reset to 1, so it would change alternatively since the test goes for a long time. Okay, so everything works as intended. So what is probably the problem now is a problem with timing, and this will be a little bit more difficult to debug. So I will reset this one as top. That is frustrating. I cannot click on anything here. Okay, maybe here. Where is it at this bench? I cannot right click on this. This is the power of settings. It needs closing simulation. Let's wait for, I'll take a quick pause and come back like in a minute. So if it's still like that, I will kill it. Oh, damn. It's okay now. I'll just restart this and set it as stop and then take just like a minute and come back. Okay, good. I'll be back. Okay, so let's do this. Let's open the test bench and let open the multipliers. Okay. So I think there's a problem in synchronization. So we have all of these signals here. Wait a second. So can I draw with a free pen on this software? Okay, let's do something like this. And let's take a pic. Whee! Okay, so this here will generate delays from the moment value change with my inputs over there and my outputs. There will be delays. And for some reason, we have something happening, and I think we saw it was in both of these two modules here. those two modules add either nothing at its output or the wrong value at its output and no shifting or growing as the addition should perform. So there's something wrong um, between the interaction of these here and this over there back like this. Oh no, sorry. Let's go back. I cannot. There is. Damn. Okay. So let's just take a new snip for a second, like this, and let's open Paint. So I will be able to do some Control Z. Sorry. Okay. But now this occur a delay. This occur a delay because of those clocks. This also. This goes round like this. And there is also a delay here. Okay, so one of the things we could try to look up is these two here, 3 here, up to the output of the output of the cell. So now that I'm thinking about this, it's normal that we have a 0 quickly because we have only 3 ones. So I think there might be something correct with what we started, but we should see the shifted values. So those values here, we saw in test that the Q changed, but it's like the out didn't. Okay, so let's create. We could create a test bench that take those 3 together and look at the output over there. Okay, let's try this. So we go back here. We create a new simulation. Let's call this a TB, like so the iterative part of generating the numbers that we accumulate. So the shift and add. So shift and so it's just the shift here. In fact, it's just the shift. So TB shift, okay, finish, yes, yes. Okay. So what I'm currently doing is trying to do baby steps, and the project I did in the past, and often so the picture processing unit I did for one of the class I teach at the university is we didn't have much registers to keep. Pretty much everything was without a clock except one module, so it was quite fast. And this is the first time I have a project where a lot of modules will have clocks and a temp, like an internal register that keeps a value. So we will have to deal with this and learn together. So shift register. Let's take a look at this one, in fact, and we will copy the shift here. So with the multiplexer, the shift, and the serializer. Like so. Let's go back to our test bench and copy all of this here. Okay, so I will take a sip of water. Good. So now data, those two data, their signals A and B. So let's create signal SA that is an SB. Both are STD logic vector. See, it's 7 down to 0. And let's instantiate them to zeros, like so. Okay. Now, load both our component uses the same load and compute. So signal load, S compute will be STD logics, so single wires, and equal to 0. All right, now we have the clock, so let's the clock also start to 0. Sorry about that. Vivado crashed. Okay. We need to get a lot of patience. Right. So now CLK, the clock is set to 0 at start. Good. Then we will have the Q of the serializer, the Q of the shift register, and we have the Q of the multiplexer. And so the okay, yeah, and the Q here will go to the cell here. In will receive it's the shift, so the Q here. We need to set a 0 here. We then need a constant S0 2 dot std logic will be equal to 0, and this will go there, and the Q will be the signal we want to so we will signal S shifter, S shifting, and S val. So this is the shifter, this is the shifting, the Q, I mean, and this is the val. Those are all STD logic vector 15 down to 0. Good. So create UUTs. We will have the serializer. Port map. This, the serializer, if I go back here, it's the operand 1, so I think I call it B, SB. Then we have S load, S compute, and S shifter. UUT1 is the shift register. Port map. What's the problem with this one? SA, S load, S compute, S shifting. Current type expected. Oh yeah. So this is only 1 bit. And this near S shifting. Okay. Current type logic vector expected shift. Load data. Ah, there is a CLK. SCLK, SCLK, good. Okay. And now we need the multiplexer. So UUT2, port map. Now okay, it's zeros here, and it's SCD logic vector down to 0. And it is this other, because now we have S zeros. So it's the 0th index of the mux, and when we select 0, we want all zeros. S shifting, this is the value that is shifting, considering the shifter. And we have the select, so it's S shifter, which gives us a 0 or 1. 1, it means we want the shifting. 0, it means we don't care. And not we don't care. We want the value of the shifting, and we need the output. The output was an sval. Good. We need a clock process. Y process, begin and process. We say constant period, time, then an S. So wait for period divided by 2, S CLK, receive not S CLK. Good. Process, begin and process. So we want to set SA SB and load compute. The clock is already so SA SB. Let's set a value. So those are 8 bits, I think, right? Yeah. Yes. So let's say A5. Wait for period. SA is now 5A. SB is now 7. Sload is 1. Wait for period. Sload receive is 0. And what I will do, in fact, is so sload where do we want sload to be up for full period? That seems to be overkill, but okay, let's continue and we'll see what we'll do with that. Let me check something real quick. Okay, so I think the approach is correct. Um, so we'll try this and see where it goes, but um, let's just modify this for it's not really a big deal, but let's rising edge CLK and then do the load and the compute. So it will do the load first and then look for the compute. Let's do this also for the what is the other one? It's the sorry, not the Mux serializer. Like this. And like this. Okay, so now what is the problem? Messages, bound file error. There's syntax error. Oh, like this, and no more error. Okay, good. So now we need to set the compute to 1. Wait for period times 8. And compute to 0. If Edo crashed, it would be cool to have a crash counter. It would be great. Water. Okay, now we go to the simulation. Sim shift. Good. So now we should have something working. Let's try this. And it will be important to look at the synchronization of each steps up to the output. So here, let's zoom in. Good. So S shifting as well as 0. Okay. So this is shifting. Let's see to this is shifting correctly. This on the other end. What is this as well? This is the output. And we have only 5A, which is incorrect. Because the shifter is set to 1 for 3 clock signal. So 1, 2, 3. And then it goes down. And now as val is 0. So what's going on here? Okay. We have, I think this is a problem. There's something wrong with this part. Let's look at this. So this is SER data. surload. Sorry. Surcompute and surq. And we have the internal surreg. Okay, this is the shift. SHFT data. SHFT load. The loads and the compute should be all the same. Oh, I missed this. We don't, well, let's put at least one clock. And the Q, so the clock will go down, and this is the CHFTQ. Okay. So, and now the multiplexer, we're on the in 0, it's always 0, so we don't care. On the in 1 and the SEL and the Q. Okay. So this is the MUX. This is the MUX in cell and MUX Q. Okay. So now we see that this is when we load. So at that point here, we have SIR register here. Oh, we don't have the value. So let's rewind, replay. Okay, so this is a 7, this is a 3, and this is a 1. And we see that this yields a 1, a 1, and a 1. So we have 3 ones. This is what we want. This is working. Now, we see that the shift Q here goes from 5A to B4 to 168 to D0, 5A0, B4, 168 to D, and I guess at some point we will go back to, oh, this is a problem. We don't go far enough in the I think it's more steps than I thought. It's 9 steps. Okay, so we will look at this right now. Here we go and say 9. Maybe we don't have enough how can I say that? We maybe don't have enough steps in our state machine we've created, but we'll see. Okay. Did this work? No. Do I need to close the simulation and start it back just to make sure? Let's just rewind and go this side. It would be better. Okay. It's 6, 8. Oh, there's another 1. So 10. Damn. Let's say 12. Just to make sure. No. And oh, its compute goes to 0. Yeah. And it's supposed to be 8, but let's put 8 back and look at what's happening. I guess it's because we have a delay. We'll see. Going back at the start. I don't get to the A5. So there's 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11. But it's not normal. Something is wrong. Something's wrong. We have 8 bits. We want to shift 8 bits. It should be 8 shifts. 1, 2, 3, 4, 5, 6, 7, 8. Doesn't make any sense. Let's just draw this. We move the mic. Okay, so we know that we start with A5. So this yields 1, 2, 3, 4, 5, 6, 7, 8, 1, 0, 1, 0, 0, 1, 0, 1. Okay, so if I shift everything, I will get 1, 0, 1, 0, 0, 1, 0, 1, 0. So this is, in fact, 1, 4, A. Now, if I put another 0, we will have 1, 0, 1, 0, 0, 1, 0, 1, 0, 0. So now we have 2, 9, and 4. Now 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0. This is 5, 2, and 8. Again, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0. So this is A, 5, 0. Again, we have 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0. So this is 1, 4, 8, 0. Again, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0. We have 2, 9, 4, 0. Okay. 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0. 5, 2, 8, 0. And the last one, 1, 0, 1, 0, 0, 1, 0, 1, and all zeros. It's A500. So this is step 1, 2, 3, 4, 5, 6, 7, 8, 9. So in fact, this is like the loading stage, and all of these are the steps. But if we think about it, it's normal that we have another step, one more step, because we want to add all of these. So there might be another one of the steps that is missing. Ah, damn. Look at this. 5A, no, yes, that is the 5A we want. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So it works, but why does it? I think it's because it started. Yeah, let's go back here. We have 8. Let's put 9 just to make sure. I don't think the first one counts. Doesn't really count. Let's put 8 back and wait. And I will try something here. This is what this makes the process go indefinitely. There's a better way to change this. I'm not sure how. If I find it, I'll probably share it with you. But this can be a little bit annoying when you want to test values. Okay, so now we close simulation, just to make sure everything is fine. Run simulation. I think it looked great. I think. Plus, 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 plus. Okay. Now we have 0 here. Then we have A5, B4, 168 to D0, blah, blah, blah. Blah, 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 blah. Five A. Why is there? Okay, so this is 0, 5A, B4, 16, and 5A. And then since the compute is set to 0 here, then the shifting doesn't change. So now as val. So let's look at the shifter. So we have where is my little okay. So this shifter is 1, 1, 1. So at the output we should see at S value we should see A5 before 068, but we see only A5. Why? So we need to redo all of what we did earlier. Okay, so this is sreg of the serializer. This is the sreg of the shifter. And this is the Q of the mux. Let's look at this one. Wait. Oh. Okay. This should be okay. This is the mux. What is the cell? I don't get it. Yeah, let's save this. Yeah. Save. And do you have configuration file? Yeah, go ahead. Okay. I don't understand why this is not changing here. Like we see the mux cell is 1 all over there. We see that in oh did I think I know what's happening. Yeah. I didn't test for in 0 in 1, I think, because I just make sure the cell doesn't. But if in 0 change, I want it to change, and in 1 also. I think this is my problem. Okay, is there a way to like restart the like I don't want to, I just want to keep all of this, but redo the tests. Okay, maybe later. Let's look what's happened if I do this. So okay, I will try to close this simulation and then run simulation. Oh yeah. Look at this. The Q changes now. Good. Okay. So now we've solved one of the problem we had. Let's go back to the real test bench and see if it solved the problem. Maybe. Who knows? So we take the multiply controller, set as stop. We wait a second, we close simulation and we run simulation. Let's go back and run for the 150. What is that? Okay. So product doesn't change again. But let's look at the let's look at some so the shift here we the max 0. Is this the one we need to look up? So this is the cell. Okay, yeah, but does it change? Okay, I think it works, but why is it that long? Why is this that long? I want to see the test. Then, okay. Okay, so what's happening is we have 7 that enters as SB. So this is the value. We have a E, E, 1C, 38. The shift seems to be working. Ah, what's happening? So if I go back just to see what's happening with the other mux. Okay, so in mux 0, mux 1. So if I go back to the code of our beautiful UUT, what we see is mux is shifted and mux 1 is the full adder. Okay. So this should represent the sum and this should represent the shift. So shift. This is the full adder. Good. So let's just looking what's going on here. So we have 7. Like, so why both of them are 7? I don't get this. Why? Let's put A and B again, just to make sure this is okay. Yeah, I guess it would be both 7 since the first value to be added is 7, so it's probably okay, but it should change both to E. So do I need to go back like this? Yeah, I need to restart this. Okay. Close simulation. Run simulation. Let's go back here like this. Okay. So now we have B. Yeah, that's B. So it's everything seems to be okay. But now one of the problem I see is look how where's my clock? Clock. Okay. So we see that we see here that at the moment the select is 1 here. We have 2 clock cycles before getting, and that is what I think must be one of the major problem we have, is that we have a 2 modules with registers that will send data to the mux that is combinatory, but in one case it goes to operand 1, and the other is the sum that goes back. And I'm thinking is I don't think it should it so the time it comes and then the addition is done, and you see that the value of the FA is changing here, and it goes to 58. If I do the multiplication, B is equal to 11, and we set 7. Yes, it's 77. 77 is the value we should get at the end, but it's not 58 exa. It's supposed to be it's supposed to be, we calculated earlier, 4D. Is that correct? Yeah. Yeah. Okay, so it was supposed to be 4D, not 5/8 here. So there's still something wrong, and I'm guessing it's something about the it's something about the delay between the mux of the full adder, not the mux but the register. Okay. Okay. I want to see the load. And I want let's look at the load here, and let's say 1. Okay, so we load at that point here, but why is this at FT? Oh, okay. I don't want to do this at F. That is something I want to make sure it is a full period. Okay. The load is set. Okay, so S multiply. Okay, I want to see multiply now. Okay, so the multiply is set to 1. So the load is set at this moment in time. So there is a skewish phenomenon here, and for okay, so how can we make this? I guess when S multiply is 1, I want S load to be already 1. Okay, let's change this. So this is again in the multiplexer here. No, it's in the shift register and serializer. Okay, this. So the clock will make sure it will so the load will be set at the clock. Yes, that we don't have any choice for that. Or let's try something. Okay, we try something. Process load begin and process. So yeah, because the rising edge is the moment we look at the value. If I go back in the here, we see that the only thing we do in that test here, not the test bench or the multiple, yeah, this one, in fact, yeah, this is the right one. So when we set this to 1, then the multiplier controller here will map is because yes, this is the moment where we set load to 0. But what we would want is to make, oh damn, and this is at this moment, but let's create multiply and process and set load to multiply and remove this, remove this, this. Okay, so we would want the multiply to be asserted for a period, then shut down. I guess that makes sense. Okay. Now we go back here, we close simulation with this card. Okay. Now we stop, we close this, we make sure that this is the right test we do, yeah. So let's run. Like this, okay. Now we want the S multiply. Oh, it kept this, right? That's weird. S multiply there. So S load UIT shift is, where is my S load? Okay, so S multiply is synced with S load, which should be better around the clock. So at that point here, we see that our value are loaded. And we have that in fact the SEL is 1 for 1, 2, 3, 4. And the shift doesn't shift. Okay, let's do 120. Okay. So shifter in. Okay, the shift shifts. Yeah. Here. The multiply. Where's the compute? It's in this one. Okay, the compute start here. At that moment, so we have 1, 2, 3, 4, 5, 6, 7, 8. So the compute seems to be working, but why? And we have the compute, so we have 1, 2, 3, so 7. So compute should have 3 like sums, so 1, 2, 3. Then it shouldn't be adding here, but for some reason it does. It does add something, and if I'm looking at the mux 0 and I'm looking to its output, it should yeah, we see that it is 0 here, so this is correct. But again, we change very close to the rising edge. There's something that I don't really appreciate with that. I would prefer it to be like not that far close to the edge. I think I will need to look this up a little bit because like I said, I don't have much project where we add um a lot of signals and register to synchronize. And I'm a little lost now. Start to be late too, so I think I will end um the stream right now, and next Tuesday will, but in fact this weekend I will probably try to solve this problem before. I would like to finish it before the next stream, so we can enter the other problem where we communicate with the CPU in the FPGA. And so I wish you luck and see you next week. Bye now.